Okay, everybody. Today, I want to continue our discussion on confidence interval. But I want to probably start from scratch, almost to scratch, because I found that some of you still have some problems in understanding the basic concept. So I want to use this lecture as a summary lecture so that everybody understand the basic features of a confidence interval. And that's very important because the next step, the hypothesis testing, is basically very much related with the confidence interval. So why don't I start with our initial motivation? And everybody by now will understand our initial motivation. Our motivation is, let's say we want to understand something about population. We want to, for example, we want to know the true value of average salary of all these households in Korea, for example. So there is population. About population, we want to understand something about the population. So we have population here, and then there is some characteristic or some variable about the population, and that has true values. For example, true mean and true standard deviation. So mu and sigma is something we want to understand. But basically, we want to understand this mu value. But again, the population is too huge, so we don't have enough money and we don't have enough, time to look every single element in population. And therefore, we want to have some sample, right? Small subset of population. So we have a sample. And we know that the sample size is n, and we know that we can calculate the sample mean value, sample mean, which is x bar. And also we can calculate the sample standard deviation, which is s, not sigma, because sigma is something we do not know actually, although it's a true value. So what we want to do is, by looking at this sample, we want to make some inferences about the population. So that's our goal. That's our goal. We want to use a sample, and using the sample, we want to understand population. But there is a very interesting theorem, which we already know, which is a central limit theorem. And thanks to this theorem, we know that x bar actually follows the normal distribution with mu and sigma over root n. So you can take the square here. Okay, this is very nice characteristics. This is a very nice theorem, which enables us to use a sample to make some inference about population. And we already know that if a variable follows normal distribution, for example, if this is the case, then we can make something like this. Let's say, what is the probability? What is the probability, or the sample mean is within some range? Let's say mu minus z alpha over 2 sigma over root n, and also mu plus z alpha over 2 sigma over root n, and this is going to be 1 minus alpha. So this is a sort of a confidence interval, but not quite yet, because what we want to estimate, what we want to understand is mu, not x bar. And therefore, we need to make a certain arrangement, right? So we can make some rearrangement, and then we can convert this into something like this. Mu x bar minus z alpha over 2 sigma over root n, and x bar plus z alpha over 2 sigma over root n, and this is going to be 1 minus alpha. So now this is a very good expression because we use some sample mean, and using the sample mean we estimate the true value, which is unknown. And we already know that if a variable follows normal distribution, we actually know how we can estimate g values. Well, actually it is already well known. In other words, g alpha over 2 is, let's say, 1.645 if alpha is 0.1, right? And this one is going to be 1.96 if alpha is 0.05, and also this will be 2.576 if alpha is 0.1. So the values are well known, and if we use this value, we can actually estimate the confidence interval for mu. In other words, this equation says that when someone asks me about what is the true value, what is the range of true value, then I would tell that person the true value is between x bar minus g alpha over 2 sigma over root n and x bar plus g alpha over 2 sigma over root n. So mu is between these two values. And when I say that, how much confident am I? I'm confident at this level. In other words, if alpha is, let's say, 0.05, then this one is going to be 0.95. So what I'm saying is that when I tell someone the true value, true mean of population is within these two values. So when I say that, how much confident am I? I'm confident at 95%, 0.95. That's my confidence level. So in a sense, I already gave you the confidence interval. But as you can, guess, as you can see, the equation itself is not complete yet because this is unknown, right? This is something unknown. But we already know x bar, we already know g alpha over 2, we already know n, which is the sample size. But we do not know the true value of sigma. Sigma is also unknown. So somehow this equation is incomplete. And therefore, we need to use something else instead of sigma. And what value can we use instead of sigma? We already know that we estimate the sample standard deviation, which is S. So it seems very natural for us to use S in lieu of sigma. And therefore, we can actually convert this equation a little bit further so that now we have something like this. P x bar minus g alpha over 2 S rather than sigma over root n and mu and x bar plus z alpha over 2 S of root n. This is going to be 1 minus alpha. Now it looks great. Now it looks great because everything we already know here, x bar is known, g alpha over 2 already known, s is already known, n is already known, and mu is unknown. Therefore, what it says is that we wanna find out the range of unknown value using known values. So it is perfect. But unfortunately, it's not perfect yet because there is a slight problem. I already mentioned during the class. The problem is that if we use S here, then suddenly we may not use these values because these values assume that we have some standard normal distribution, but if we use S instead of sigma, suddenly this does not follow standard normal distribution. Actually, it follows another distribution. I already called that T distribution, right? T distribution. In other words, instead of G, we gotta use something like this, T alpha over 2. But this one is depends on the sample size. Okay, so let me just repeat what I meant by this. If the sample size is large enough, if I give you a rule of thumb, if n is larger than 100, I would say it's safe, it's okay, probably okay. You know, not exactly the same, but probably okay to use z values, z alpha 2, z over 2. But if n is small, probably less than 100, or if n is less than 30, then you must use other multiples, which is t multiples. But you know, g alpha over 2, we can get the exact values regardless of the sample size. But if we use t alpha over 2, it depends on the sample size. So let me give you some idea. How it changes. For example, we already have that g value. Z alpha over 2 is going to be 1.96 if this one. Then what about this? T alpha over 2 in case where alpha 0.05. Again, because T alpha over 2 depends on n, we gotta have this sample size. Let's say we have a sample size 10 or 30 or 40 or 50, and let's look at some other cases as well. 1,000 and the sample size 10,000. Then we want to estimate this T alpha over 2. In order to use this, I already talked about this during our last lecture. We gotta use Excel. And in the Excel function, we will have T dot inverse, and then you put this alpha over 2, which is 0.025, and then you have to put this n minus 1. So if you type T dot inverse, in other words, inverse function of a T distribution, you need to put two things. One is the probability we are interested in, and then n minus 1. N is the sample size, and n minus 1, we already learned that this is degree of freedom. So why don't you try these numbers? Why don't you try these things? So let me just give one values when n equals 10. If you use this function, if you type this in your Excel, then when the sample size is 10, the value is going to be minus 2.26216. Okay? So I want to stop here for, let's say, a couple of minutes so that you can get these numbers for n equals 30, 40, 50, 100, 1,000, and 10,000. Okay? So why don't you try T dot inverse using your Excel, and then get these numbers, so we can compare what you get with my numbers very shortly. So why don't you take let's say 5 minutes to calculate this. Okay, I gave you 5 minutes, so I hope that everybody was able to get this t multiple using your Excel, especially t dot inverse. If you still have some problem, you may welcome to ask questions to your TA, okay? Probably after the class. So if you were able to get these numbers, you probably get, let's say here is minus 2.04523. Minus plus, the sign is not important because we are looking at both sides at the same time. So this is the left-hand side, but it doesn't matter. What is important is the absolute value. And if the sample size is 40, make sure that if sample size is 40, the degree of freedom is 39, right? N minus 1. And, you know, I already explained the logic behind using N minus 1 as degree of freedom. But if you have some difficulty in grasping the meaning, you just, you know, accept this notation, so-called N minus 1 as degree of freedom, at least for now. Maybe later when we talk about some other topics, the degree of freedom will change, but for the time being, N minus 1 is the degree of freedom. So N is 40, then minus 2.02269, and N is 50, it's going to be minus 2.00958. And if N becomes 100, it will be minus 1.98422. And if it's 1,000, it's going to be minus 1.96234. And if it's 10,000, now we have minus 1.9602. So you now see why I ask you to get these t multiples for different sample size. And you see that as the sample size gets large, especially when the sample size is 10,000, the t multiple becomes 1.96, which is almost the same, when we have a standard normal distribution. But if the sample size is 10, the t multiple is 2.26, which is quite different from 1.96, right? So that's why I said that when n is bigger, n is big. For example, if n becomes 100, then it seems like the difference is not that much, right? 1.98 and 1.96. So when n becomes large, the t distribution becomes closer to a normal distribution. So it's kind of a rule of thumb. When n is larger than 100, it's safe to use g values. But if n is smaller than that, then it's better for us to use the t distribution. And you know, we already talked about the relationship between normal distribution and the t distribution. Let's say this is a standard normal distribution, and say this is 0 because this is a standard normal distribution. If this is a standard normal distribution, then we already know the t distribution will have thicker tails or heavier tails. So the t distribution will look like this. So that's t distribution. But the thing is that as n becomes larger, the t distribution squeezes, and it will very much look like a standard normal distribution as n increases. And that's the logic. And when we use t dot inverse, that is, we are looking at this cumulative distribution function, right? So that's the same thing with you know, normal distribution and the t distribution. For example, if this is a cumulative probability function for t distribution, will look like this. And what it is, this one is, first we take here 0.025, right? And then we go that way, and then go that way, and this one. So if this is going to be minus 2.26216 if n is 10. Okay. Oh, sorry. I think that you gotta look at this one. The value is minus 2.26216 if n is 10. That's what I wrote here. Okay. Okay. Now we understand, the motivation behind using t-distribution rather than, g, the normal distribution, when n is particularly when n is small, and except for the difference in terms of a shape, the logic is almost the same. Standard normal distribution, t-distribution. So using cumulative probability function in order to estimate these values, that's the same also, right? There is no difference between normal distribution and t-distribution. So I hope that this will help you to understand why we needed to use t dot inverse function. And I hope that you now understand how to calculate these t multiples. Now, because we have a good idea about all these logics and theories, I want to continue our example. I want to continue our example. This is a battery life of iPhone 5 or iPhone. So why don't we start this example? Well, actually, I gave you this as an assignment to you. So I hope that everybody already know what it is.